Hello, my name is Steve Miller. I'm a math professor at Williams College, and I'm looking forward to year 2 of the PolymathJr REU project. So I'm going to talk a little bit about the number theory group that I'll be leading, and this is building on joint work that I've done with many students over the years, both in Polymath last year and in more traditional REUs like the one we run at Williams College. Because of that, I don't want to go into too much detail about the projects because some of these are ongoing with various students. But if you want more details, I and the students are happy to chat. Many of them are excited about coming back to the Polymath Junior program as mentors. My email address is over here, as well as web pages to my homepage with a lot of slides, talks, and papers. Okay, so here, you feel free to hit pause, is a rough sampling of the different types of projects I'm looking at. And the reason this list is so long is that with so many people working in the group, we have the wonderful opportunity of splitting into smaller groups depending on what people are interested in. And so I'll talk a little bit about each one individually for a little bit. So the first is on Zeckendorf games. And again, as I mentioned, this has led to a lot of publications with students, including those from the PolymathJr REU last year, and they're happy to continue. So very briefly, what is the Zeckendorf game? So we'll take the Fibonacci numbers 1, 2, 3, 5, 8, 13, where each number is the sum of the previous two. There's a reason we start with 1 and not 0, 1, 1. And we have two different rules to combine things. So if I have two pieces on one of the bins, so my bins are 1, 2, 3, 5, 8, so on, the Fibonacci numbers, I can replace 2 on bin n with 1 on bin n plus 1 and 1 on bin n minus 2. I have to be a little bit careful because I don't have bins below 1. So if I have 2 on the 1 bin, that's the same as 1 on the 2 bin. And the other thing I can do is I can replace fn and fn minus 1 with an fn plus 1. So for example, if I start with the number 10, the only move I can do is take 2 1s and make a 2. So now I would have 8 here and 1 here. I could take 1 from the 1 bin, 1 from the 2 bin, and make 1 on the 3 bin. So this 8 would go down to 0. This 1 on the 2 bin would become a 0, and this would become a 1. Or instead of doing that, I could take 2 from the 1 bin and make another 1 on the 2 bin. So I could now have 6, 2. And what you can notice is 6 times 1 plus 2 times 2 is still 10. Again, now I could take something from the 6 and something from the 1 bin, something from the 2 bin, and make a 3. And so if I do that, I would have 5, 1, and 1. And notice it still adds up to 10. Now I could take 2 things from the 1 bin and make something on the 2. I could take a 1 and a 2 and make a 3. Or I could take a 2 and 3 and make a 5. Let's do that. So we have 5, 0, 0, 1. Well, at this point, the only thing I can do is take 2 things from the 1 and make something on the 2. So it'd be 3, 1, 0, 1. I could take something from a 1 and a 2 and make a 3. So it would be 2, 0, 1, 1. 5, 8, so that's up to 10. I could combine the 3 and the 5 bin and make an 8 bin. 2, 0, 0, 0, 1. And now the only move left is to take the 2 here and make it into 1 over here. So I'd have 0, 1, 0, 0, 1. And what's interesting is the game has terminated. And you can prove that the game always terminates. We have great bounds on how many moves it takes. And we can actually prove that if you alternate turns, player 2 has a winning strategy. But what is truly amazing is it is an existence proof. We don't know what that winning strategy is. And so the biggest goal would be to try to figure out what is that winning strategy. Other goals would be to try to generalize this to other sequences. So that's one possible project. Another possible project is on noncommutative avoidance. And so this is basically constructing sequences that miss certain sequences. So for example, let's say I want to construct a sequence that doesn't have any 3 terms in geometric progression. So geometric progression would be 1r squared. Or more generally, a times r squared. And if they're all integers, what's interesting is that r does not have to be an integer. So I could start off with 4. I could multiply by 3 halves, and then I would get to 6, and then multiply by 3 halves again, and I would get 9. So the ratio doesn't have to be an integer, even though all the terms are. And you could ask, well, what is the densest sequence you could construct? So if we have our sequence, A1, A2, A3, ... and we don't have any 3 terms in geometric progression, we could ask for maybe count, get the limit as n goes to infinity of an over n, and see, what fraction of the integers do we take up from this? And the question is, how do you construct something like this? I might say, well, let me start off with 1, and I'll do a greedy algorithm approach. I'll put in 2, I can put in 3, I can't put in 4 because then 1, 2, 4 would be an arithmetic progression. So I put in 5. I can put in 6. Well, no, let's see, if I put in 6, 1, 2, 6 is not a progression. 1, 3, 6, it's not a progression, so that's fine. I could put in 7. I could put in 8. I can't put in 9 now because 1, 3, 9. And so this is a greedy approach. And you can analyze what do you get from the greedy approach. Is that the best? How close is it to what's best? And then how can you generalize this to other settings? And so I've had some students work on non-commutative setting on this problem. And there's a lot of fun things there to pursue. Another possible project is generalizing the Mordell-Weil group for elliptic curves. So for elliptic curves, we have the form, y squared is x cubed plus ax plus b, where a and b are integers. And if you want to plot what that looks like, if you looked at y equals x cubed plus ax plus b, that would be a cubic, and it might look something like this. But now if I look at y squared, well, y squared can never be negative, and so that's going to then lead to a plot that will look something like this maybe. And so we have something looking like this because the negative regions are inaccessible. And it turns out that you can make a group structure on something like this. And so just very quickly, if I have something like this, I can take 2 points, say P and Q, and I can draw the line that connects them. And I can look and see where does that line hit. And it turns out if you then reflect where it hits, if you call that P plus Q, you get a group. And it turns out it's a commutative group, which means P plus Q equals Q plus P. Well, it shouldn't be too surprising that this is a commutative group because we define the construction of addition geometrically by drawing a line. So clearly the line connecting P and Q is this line that connects Q and P. It's non-trivial to prove that it's associative, to prove associativity. But it turns out that there is a beautiful group structure. And if we let E be the elliptic curve y squared is x cubed plus ax plus b, we let EQ be the set of all pairs x and y. X and y are rational, and y squared is x cubed plus ax plus b. So it's all the points on the elliptic curve with rational coordinates. It turns out that this is a group, and that's the commutative group we're talking about. So if P and Q have rational coordinates, so is P plus Q. And the reason is, if you look at this line as y equals mx plus b, if P and Q have rational coordinates, that implies m and b are rational. So if we then try to find the third point that satisfies y squared is x cubed plus ax plus b, we would get mx plus b squared equals x cubed plus ax plus b. So we get a cubic x cubed minus mx plus b squared plus ax plus b. And we know, say, xp and xq are 2 roots. And so the third root has to have rational coordinates as well, because everything on the left-hand side is rational, xp and xq are rational. Therefore, xpq has to be rational. So the question I want to investigate is, what can you say about similar groups in other settings? And we can start off with the circle group, x squared plus y squared equals z squared. You might remember this from the Pythagorean formula. And we can talk about how this varies as you change and look at other number fields. And then the last thing, which I don't want to go into too much detail here, is just some general problems on L functions and random matrix theory. These are going to be a bit more involved in terms of what the background is. For these projects, it would be very helpful to have seen some complex analysis or some advanced number theory. But if people are interested, I'm happy to chat a little bit more about what might be possible here. Anyways, thank you for your time and hope you have a great day.